Swayam Prabha. Digital India. Educated India.
Hello everyone, this is lecture 4 of module 3. So in the previous lecture we discussed about the phenomena of dispersion where we defined a term zeta and we saw it's dependent on the tangent term where we saw the graphical solution of the dispersion modes where we defined n is equal to 0 for the fundamental mode and there were some higher modes as well. In the lecture today, we are going to further build upon the previous lecture and will discuss about the dispersion and associated phenomena such as the phase velocities and the group velocities. So, the concept that we are going to cover today will be the dispersion and the phase and the group velocities. Before we even go into defining those two terms for the phase and group velocity, let's understand what dispersion means. So there are two basic terms that we generally encounter with. One is the physical dispersion, another is the geometrical dispersion. So as per the Snell's law, when light passes through a prism, this is your prism, and when light falls on this prism and this light has a constant frequency but it has different components consisting of variable wavelength. When it falls on the prism, then due to the refraction this light gets deviated into different angles due to the phenomena of refraction because of the varying wavelength. And this particular phenomena where the light gets deviated into different angles and gets distributed in the form of different colors is known as dispersion, and in the case of light it is known as physical dispersion. So this is the phenomena of physical dispersion. But in the case of Earth, what actually happens is that due to the shape of the Earth is curved on the surface, and as you go deeper down, the velocity of the material gets increasing. So because of that, the phenomena of dispersion happens, and if it is happening in the case of love wave, then it is known as love wave dispersion. And that particular phenomena of dispersion, because of the geometry and the depth the velocity is increasing, is known as the geometrical dispersion. So the phenomena of dispersion that is taking place in the case of the Earth is known as geometrical dispersion. So what we can say, in the case of light, the speed of light in a medium or maybe like in the water is often frequency dependent. So if you look at the raindrop, then when the light falls on the raindrop, then it gets refracted into different colors by different amount, and then it gives us a rainbow. So that particular phenomena is basically known as physical dispersion. And if we define it more technically, then the dispersion is basically the velocity of the waves in the dispersion is dependent upon the wavelength, or you can say different wavelength in a wave travels with different velocities. Now, if we talk about the phase velocity is a function of two parameters, that is the angular velocity and the wave number, and we can define it as the ratio of the angular velocity to the wave number. And in the dispersive medium, this angular frequency also varies with wave number. So for instance, if we talk about the short period tsunami wave, then it follows omega is equal to under root of g and k, where g is the acceleration due to gravity, k is the wave number, and we can solve this in terms of velocity, such as v is equal to omega yk, that omega can be further equated to omega is equal to under root of gk, that is under root of gk by k. So if we want to write this particular relation in terms of dispersion, then it can be written in the format as f as a function of omega comma k is equal to 0. So for tsunami dispersion, it can be represented as omega minus under root of gk, that is equal to 0. Now, if you want to further explore the phenomena of dispersion, then we can consider two harmonic waves. If you just want to have more insight into it, then in the case of Earth, what happens that the velocity is increasing downward, and when there is a shear wave that is traveling, then it gets multiply reflected from the surface of the Earth, and these multiple reflections get superimposed with each other and can give waves such as SS wave, SSS wave, SSS waves, and likewise multiply reflected shear wave. Those will further give rise to the development of the love waves. So there will be a slight change in the angular frequencies and the wave number between these waves before they superimpose. So let's consider a very simplest example to understand what is dispersion and what are the phase and group velocities. So in order to do so, let's consider two harmonic waves with slightly different frequencies and the wave numbers. So let's suppose one wave has angular frequency omega 1, another has angular frequency omega 2. Omega 1 is omega naught plus delta omega, where delta omega is basically very less than omega. So here we are defining two harmonic waves with slightly different angular frequencies and as well as the slightly different wave numbers, where the wave number of the first wave k1 is equal to k naught plus delta k, k2 is equal to k naught minus delta k. So here you can see delta k is also very less than k naught. So in order to have the superimposition, then we can write the total displacement due to these two waves having angular frequencies omega 1 and omega 2, wave numbers as k1 and k2. So we can just sum up their displacement to get the net displacement of the two waves. So this u is basically defining the net displacement or the total displacement due to the superimposition of two waves. So when we sum those waves up, and we can get cos k1x minus omega 1t plus cos k2x minus omega 2t. So if you remember, we considered two simple harmonic waves, so that is why we are representing that these two waves as the cosine waves having the parameter as k1 and omega 1. Another cosine wave is having the parameter k2 and omega 2. And when we put up the values that we saw earlier, these two values, then what we can see, k1 can be replaced by k naught plus delta k, and omega 1 can be replaced with omega naught plus del omega. Likewise, k2 can be replaced with k naught minus del k. Similarly, omega 2 can be replaced with omega naught minus del omega. So when we do so and do some rearrangement, then what you can get that there are two terms, kx minus omega t, and there is another term del kx plus del omega t. So you can simply say that it is nothing but it is the form of this particular trigonometric identity, where it is said that cos theta plus phi plus cos theta minus phi is equal to 2 cos theta cos phi. So the net displacement will become u is equal to 2 cos kx minus omega t, cos of delta kx minus delta omega t. So this is nothing but is a product of two cosine waves. You can see there is one cosine wave of having this one expression, and there is another cosine wave having this one expression. So the wavelength of the first wave is nothing but this is 2 pi by k, and where delta k is very less than k, and the second wave is having the wavelength lambda is equal to 2 pi by delta k. So this is the second wave and its phase is like this. So that is how we can define two waves. One is having the wavelength 2 pi by k, another is having the wavelength lambda is equal to 2 pi by delta k. So what we can see, if you look at that expression again, let me rub it up to show you clearly. So you can see there is this term which basically represents the carrier wave, and there is this term, this is another harmonic wave that represents the envelope wave or the velocity of the envelope. So you can see the velocity of this particular carrier wave will be omega by k, and velocity of this particular envelope wave v will be equal to del omega by del k. Now let's have the graphical representation of these two waves. Let's suppose in figure A, you can see there is one wave that is a cosine wave that can be represented as cos omega 1t minus k1x, where omega 1 is omega plus del omega, and wave number k1 will be equal to k plus del k. And there is another wave that is having slightly different angular frequency and slightly different wave number. So that will be having the cosine wave something like this. When you add them up, their displacement will be added up, and you can see the resulting wave as the product of two cosine waves, and that can be represented as like this. So you can see there is this wave that is the envelope, and there is another wave that is your carrier wave. This is our carrier wave. So you can see that we have plotted this envelope and the carrier wave at three different times, t1, t2 and t3, and you can see when we are joining the envelope velocity of the envelope wave with corresponding t2 and t3 times, then you can see this is the particular line, and here for the particular frequency or the particular carrier wave when we are joining, then it basically joins like this. So you can easily see that the carrier wave is having the higher velocity than the envelope velocity, which means that she should be greater than u. So at different times you can just connect the points up for the same point as in t1, t2 and t3, and can have a feeling that how the velocities are moving for the carrier wave and the envelope wave. Now, so what we can make out from this particular figure is that the first cosine term defines a wave that is known as carrier wave that is modulated by a slower varying envelope. So that is what we see. We saw that the c is always greater than u. Since the velocity with which a wave defined, if you are defining the wave as this, u is equal to cos ax minus bt, then its velocity will be b by a. So the velocity of the carrier wave is v is equal to omega by k, and the envelope wave will be d omega by dk. That is what we have seen here. So velocity of the carrier wave is omega by k, velocity of the envelope wave is del omega by del k. Now, if we refer the former, the carrier wave velocity as the phase velocity and the envelope wave velocity as the group velocity, and can represent the phase velocity by c and the group velocity by capital U. The relationship for the phase velocity and the group velocity can be written as small c, that is basically the phase velocity, that is equal to omega by k, and the group velocity is represented by capital U, that is velocity of the group, that is del omega by del k, and can be defined for the dispersion relationship where the angular frequencies varies with the wave number, that is omega is equal to omega as a function of wave number. If suppose we are taking the del omega del k tending to 0, if it is for, we are taking the infinitesimal really small changes, then delta term can be replaced with d, that is d omega by dk. That means the your group velocity will limit to d omega by dk. So if suppose we are having any anisotropic velocity structure, then the group velocities and the phase velocities will be having slightly different direction. So that is what it is written. In a medium with anisotropic velocity structure, the group and the phase velocities actual may have slightly different directions. So the phase velocity can be written as omega as a function of k by wave number. And if we want to find out the relationship between the phase velocity c and the group velocity u, then it can be traced as like this, where let's suppose u is equal to d omega by dk, and omega can be written as ck, d by dk and ck. When we differentiate ck with respect to k, then we can use the chain rule. Then what you can get is k dc by dk plus c dk by dk, and this will be equal to 1. What you will get is c plus k dc by dk. So in terms of wavelength, if you want to find out, then you can just take lambda is equal to 2 pi by k, and it can be used to derive the group velocity equation. Now let's suppose dc by dk can be written as dc by d delta and d delta by dk. We are just cross multiplying d lambda on the numerator and the denominator. Then what you will get is dc by d lambda, and then you are just writing lambda is equal to k upon 2 pi. I'm sorry. So here the k is equal to 2 pi by lambda. K, when you will put that into this equation, what you will get dc by d lambda in bracket minus 2 pi by k square. And now we can convert this into wavelength. So k, if you remember the previous relation, k dc by dk plus c, that is equal to u. So when we rewrite it, that is basically your u. So that is u. So when you will rewrite it, dc by dk, we can replace it with this term. Then what you will get is this. And then finally, the term u is equal to c minus 2 pi lambda dc by d delta. And for the simplicity purpose, we just ignore 2 pi. We just do not use 2 pi. Then the final term that we get is u is equal to c minus lambda dc by d delta. So if you look at the real earth situation, the velocity tend to get higher and higher as the depth increases. So you can also say that that the dc by d delta is greater than 0. So that is why, because as you go deeper and deeper, the higher values of the wavelength are sensitive to the higher depth, which means that dc by d delta will be greater than 0. If that happens, then this particular term will get greater than 0, which means that using this term we can conclude that u will be less than c, or you can say the c is greater than u. So that is what it is written. For an average earth, this condition must hold true. So if you look at this particular graph, you can see that in this graph we have plotted velocity, or you can say apparent horizontal velocity with respect to the period, and these are the plot for the phase velocity and the group velocity. For the phase velocity, if you will look at it, they are generally higher than the group velocities. And this graph is plotted for love wave dispersion curves, and the average parameter that we took for the earth is the beta 1 is 3.9 km per second, beta 2 as 4.6 km per second, and the density of the slower material above the half space is 2.8 gram per centimeter cube, and the density of the half space is 3.3 gram per centimeter cube, and the height of the slower velocity material, or the thickness, is 40 km. So if suppose the medium is non-dispersive, then in that case what will happen? The dc by d lambda will become equal to dc by dk, or you can say in this case where u is equal to k dc by dk plus c, this particular term, because the medium is non-dispersive, so that means velocity will not be depending upon the wavelength or the wave number, and this particular term will become 0. So in that case this u will become c. Or also if you will look at particularly this term, then in that case dc by d lambda will become 0 in case of non-dispersive medium, and then finally what you will get is u is equal to c. So that is what it is written here, dc by d lambda in case of non-dispersive medium will be equal to dc by dk is equal to 0, and the phase velocity and the group velocities will be same. So these are the references, and in the next lecture we will further dig down into the surface wave, and will talk more about the dispersion, especially tsunami, and also we'll see some real data examples of the surface wave, and we'll talk about how the filtering can lead to give us an idea about the velocities of the envelope carrier and the carrier wave velocity. Now that is all for today. Thank you so much. Bye bye.